The study of enhancing maneuverability in a variable wheelbase wheeled mobile robot through dynamic steering curvature control. In this study, we explore the capabilities of the self-reconfigurable 6-wheeled mobile robot, JFR, which serves as a prototype for the Mars rover. The experimental setup involves subjecting the robot to various terrains, particularly the simulated Martian loose soil terrain known as HIT, MSS-1. The investigation is organized around simulated experimental tasks aimed at enhancing the robot's maneuverability. Two steering models, namely the developed 3D Ackerman and the presented Ackerman drifting models, are utilized to improve the robot's steering motion. The experiments were conducted in the ROST-Dyne platform, consisting of 5 tasks. In the first task, the motion performance of the robot's variable wheelbase length, with and without the presented wheel velocity compensation control for the wheels, was evaluated through a single-sided suspension with varying during the robot's steering motion. Furthermore, to evaluate the function of dynamic steering curvature changing on the motion trajectory, tasks 2 and 3 were conducted to concentrate on a double-sided suspension with variable while the robot was in steering motion. The 4th and 5th tasks were dedicated to evaluating the effectiveness of drift steering motion generated by the built Ackerman model with dual instantaneous center positions. Transitioning to the physical experimental tasks, we have utilized 5 distinct inverse kinematics models to analyze the control performance of the robot's steering motion on loose soil terrain. These models include the Ackerman model with symmetrically distributed wheels, the Ackerman model with asymmetrically distributed wheels, the differential velocity model, the crabbing motion model, and the equivalent bicycle model. Each model offers unique insights into the robot's capacity to navigate and adapt to challenging environments. In conclusion, this comprehensive exploration illuminates the adaptability and control performance of the HIT MR2 robot across varying terrains, providing valuable insights for the development and optimization of mobile robotic systems. The study significantly contributes to the expanding field of robotics and holds promise for informing future missions in extraterrestrial exploration. In this study, a dynamic steering curvature (DSC) control method is proposed to enhance maneuverability in tracking curvilinear trajectories for a VW WMR. The achievement of DSC control is utilized through 2 different approaches: variable wheelbase length and drifting motion. To achieve the first control approach, the variable wheelbase length is incorporated into the built 3D Ackerman model of the robot, taking into account the lifting motion of the robot box. In consequence, to change the subsequent curvilinear trajectory inside or outside of the originally planned trajectory, the instantaneous center (IC) radius of the built Ackerman model can be controlled with the variation in wheelbase length. Furthermore, in the second approach without the consideration of variable wheelbase, the wheels are divided into 2 parts to establish 2 sequent ICs of the presented Ackerman drift model. This enables the robot to generate a sliding motion effect and control the position of the subsequent motion trajectory. To validate the effectiveness of the proposed DSC control method, the ROST-Dyne Vortex simulation platform is utilized, using a VW WMR with actively and passively archived suspensions, JFR robot. It is worth mentioning that this robot is the prototype of China's Mars rover. The enhanced maneuverability of the robot is demonstrated by the results from the simulation, and the subsequent motion trajectory of the robot can be controlled effectively inside and outside of the originally planned trajectory. Moreover, to characterize the maneuverability of the robot controlled by the Ackerman model during steering motion on loose soil terrain, physical experiments were conducted with the JFR robot at a Mars surface simulation site, comparing it with the other 3 kinematics models as follows: differential velocity, crabbing steering, and equivalent bicycle model. Taking into account the variation in the heading direction of the robot during steering motion, the robot controlled by the Ackerman model demonstrated a comprehensive advantage, as indicated by the results in shorter run time, moderate travel distance, and moderate force variation on the wheels. The mechanical structure of the self-reconfigurable 6-wheeled mobile robot with active and passive suspension rockers are shown in this figure. In detail, The configuration of HIT MR2, as shown in this figure, is similarly aligned with the mechanical structure of the robot introduced in 1. HIT MRI with an industrial computer, Beckhoff C6930-0060, situated within the body box, 12-brush DC motors, Faulhaber 3056K024B, K1838, in the wheels, 6 incremental encoders, Faulhaber IE3-1024L, 8 absolute encoders, WMR 232 RTU 1224M6, 3 binocular cameras, ZED2, 3 LiDARs, Livox Horizon, and 6 6-axis force/torque, F/T, sensors, SRM3616C. Measurement ranges of the F/T sensors are as follows: Fx/Fy is 2700 N, Fz is 4000 N, Mx is 180.0 Newton meters, My is 180.0 Newton meters, and Mz is 144 Newton meters, of which accuracy is 0.04%, 0.02%, 0.06%, 0.13%, and 0.03% Fs, respectively. The Vortex Real-Time Interactive Dynamic Simulation System is capable of employing accurate dynamic modeling and real-time simulation development of physical and mechanical systems, including ground vehicles, surface and underwater robots, and aerospace. To simulate the ground scene of planetary exploration, the wheel-terrain interaction model has been integrated into a developed version of Vortex, ROST-Dyne. This study further develops a new control module for the multimode motion of a planetary rover in ROST-Dyne. The structure of the simulation platform includes a robot model, terrain module, wheel-terrain interaction calculation module, physical simulation engine module, as shown in this figure. Furthermore, the experimental terrain involves simulated Mars star soil. The physical parameters of the Mars soil simulants as shown in the table. Point 1. In the simulation experiments, the preset motion trajectories of the robot are shown in this figure. In Task 1, 2 types of 90-degree left steering maneuvers were executed by the HIT MR2 robot, with a decrease in the wheelbase length on both the left and right sides of the body. Meanwhile, these maneuvers were carried out both with and without the implementation of the presented velocity compensation control algorithm for the wheels joined at the active rocker arm. During the steering motion, a decrease in the wheelbase length on the inner side of the robot allowed an increase in steering curvature, leading to the movement of the trajectory towards the inner side of the original trajectory. In contrast, a reduction in the wheelbase length on the outer side of the robot enabled a decrease in steering curvature, resulting in the movement of the trajectory towards the outer side of the original trajectory, as shown in these videos. In addition, the degree of these movements in position deviation was augmented through the application of the wheel velocity compensation control algorithm. Therefore, to dynamically adjust the position of the subsequent trajectory, flexible control of the robot's motion can be achieved by altering different sides of the wheelbase length. Furthermore, the travel trajectory proves that the change in wheelbase length was successfully achieved using the built 3D kinematics model, and the velocity deceleration of the front wheels with the reduction in wheelbase length is accomplished through the velocity compensation algorithm. Task 2 was executed to demonstrate the impact of varying the robot's wheelbase length on its steering motion performance. In addition, the utilized 3D Ackermann model maintains a constant instantaneous center position, despite changes in the wheelbase length. To ensure the robot performs the entire process with different wheelbase lengths during 180-degree steering movements, different angular velocities were set for the active suspension rockers. The initial wheelbase length of the robot was set at 750 mm, with angular velocity values of the active suspension rockers set to 0.1, 0.2, and 0.4 radians per second, controlling the variation in wheelbase length to 730 mm, 658 mm, and 447 mm, respectively. With a reduction in wheelbase length, the endpoint of the travel trajectory shifts toward the inner side compared to the trajectory of the robot with a fixed wheelbase length, as demonstrated in the accompanying videos. Additionally, it was observed that larger variations in wheelbase length resulted in greater deviations in the endpoint of the trajectory. To further analyze the effects of instantaneous center variation on steering performance, Task 3 was conducted to achieve dynamic control of the instantaneous center position of the Ackermann model in conjunction with changes in wheelbase length. Throughout the entire motion process of 180-degree left steering, where the instantaneous center position changed with varying wheelbase length, the trajectories of the three different wheelbase length values consistently appeared on the inner side of the travel trajectory compared to the movement with a fixed wheelbase length. Conversely, for steering motion with a constant instantaneous center position, the trajectories were initially observed on the outer side and then transitioned to the inner side of the travel trajectory of the fixed wheelbase motion during the motion. At the endpoint, all trajectories were observed on the inner side, as illustrated in the accompanying videos. In Task 4, the sequence radii of the instantaneous center in the built Ackermann drift model were set as follows: 6670, 2670 mm with an angular velocity of the robot body steering of 0.3 radians per second, 5000, 3000 mm with a steering angular velocity of the robot body of 0.5 radians per second, and 5000, 3140 mm with a steering angular velocity of the robot body of 0.7 radians per second during the steering movements. The proposed drift motion model successfully adjusted the endpoints of the travel trajectories to the inner side of the reference trajectory, with instantaneous center radii set at 3,577.0 mm, 1,390.0 mm, and 913.0 mm, respectively, as depicted in the accompanying videos. The trajectory results demonstrate a linearly increasing relationship between the variation in the steering angular velocity of the robot body in these experimental trials and the decrease in the deviation value of the trajectory endpoint position. During the motion process, the robot initially performed Ackermann steering with a constant instantaneous center position, paused in 9th second, adjusted the wheels to rotate to the target orientation according to the built Ackermann drift model with dynamic instantaneous center positions, and then commenced drifting in 13th second. In Task 5, the sequence radii of the instantaneous center in the Ackermann drift model were set to 4,000, 6,000 mm with average angular velocities of the robot body steering at 0.4 radians per second, 0.5 radians per second, and 0.6 radians per second. The proposed drift model successfully shifted the endpoint of the trajectory to the outer side of the trajectory, where the instantaneous center radius was only set at 4,000 mm, as demonstrated in the accompanying videos. This suggests that the variation in the steering angular velocity of the robot body for these experimental trials exhibits a linear relationship with the change in trajectory endpoint position, consistent with the corresponding results in Task 4. During this motion process, the robot initially executed Ackermann steering with a constant instantaneous center position, paused in 8.7th second, adjusted the wheels to rotate to the target orientation according to the built drift model with dynamic instantaneous center positions, and then began drifting in 12th second. Above all, the control performance of the dynamic steering curvature on changing motion trajectory has been proven by 5 experimental tasks. The corresponding control regular of the variable wheelbase control and drift motion are listed in Table 2. In specific, for the robot motion, the new trajectory can be moved inward related to the original trajectory by decreasing the wheelbase length on the left side of the body with the developed 3D Ackermann model, decreasing wheelbase length on both sides of the body with the movement of the instantaneous center position in the developed 3D Ackermann model, and the inner trajectory changed motion with the presented Ackermann drift model. In contrast, the new trajectory can be moved outward related to the original trajectory by decreasing the wheelbase length on the right side of the body with the developed 3D Ackermann model, and the outer trajectory changed motion with the presented Ackermann drift model. In addition, the new trajectory can be moved initially outward and then inward related to the original trajectory by decreasing wheelbase length on both sides of the body without the movement of the instantaneous center position in the developed 3D Ackermann mode. In the physical experiments, 5 different inverse kinematics models are utilized to investigate the control performance of the robot's steering motion on loose soil terrain. The robot executed a steering motion with a 45-degree angle using the following models: Ackermann model with asymmetrically distributed wheels, referred to as AMADW, Ackermann model with symmetrically distributed wheels, referred to as AMSDW, equivalent bicycle model, referred to as EBM, crabbing motion model, referred to as CMM, and differential velocity model, referred to as DVM. These experiments were conducted on the same loose soil terrain. To ensure a fair comparison of motion performance under identical environmental conditions and control settings, a predetermined target position for the robot's left front wheel on the terrain and a 45-degree target steering angle for the robot body were used as the motion objectives for ending the movement. It's noteworthy that the motion characteristics of the crabbing motion model, CMM, do not alter the heading direction of the robot body, and this consideration is taken into account during the comparison of motion performance among the different models. The travel trajectory of the robot is depicted in the accompanying videos. In the case where the robot exhibited the shortest travel distance, employing the CMM control mode, this outcome aligns with the mathematical principle stating that the shortest distance between 2 points is a straight line. In contrast, the robot traversed longer distances when utilizing the AMADW and EBM control modes. In addition, the robot achieved intermediate travel distances when employing the AMSDW and DVM control modes. These instances underscore the variability in trajectories that can be attained by the robot through the utilization of different motion models on loose soil terrains. The run time and travel distance for the 5 inverse kinematic model controls in the HIT MR2 robot, as shown in Table 3. In conclusion, simulation experiments are conducted with the HIT MRI robot on the ROS9 Vortex platform to prove that DSV control can be effectively achieved by changing the wheelbase length on one or both sides of the robot body. In addition, the movement and stillness of the instantaneous center position is also taken into account in these tasks. Furthermore, the presented Ackermann drift model has been proven feasible in achieving DSV control by the following 2 tasks. These simulation results demonstrate that the motion trajectory of the robot can be changed flexibly to inside and outside directions with the DSV control. Furthermore, in order to demonstrate that the Ackermann model is better suited for the robot's steering motion on loose soil terrain compared to other motion models, the robot utilizes 5 different kinematics models to perform a physical steering experimental task. These models include the Ackermann model with asymmetrically distributed wheels, the Ackermann model with symmetrically distributed wheels, the equivalent bicycle model, the crabbing motion model, and the differential velocity model. Compared to other models, the efficient motion performance has been obtained by the robot with Ackermann models, including a shorter run time, moderate travel distance, and moderate variation range in forces on the wheels, taking into account the change in the heading direction of the robot.